Right. Hello dear students. So previously we discussed about chemical equilibrium. In addition to that introduction part of chemical equilibrium, we are able to discuss some more concepts. The equilibrium constant Kc and Kp, how we'll write for the equilibrium reactions, that will be discussed. So then again we have to write the Kc and Kp equilibrium constants, and so what are those units for the equilibrium reactions, how we have to express, and what is the relation between them, and what are the characteristics of these equilibrium constants we have to discuss, right? So Kp and Kc are the equilibrium constants, right? So by considering one example, so what is meant by definition of Kc means, that is the product of concentration of products, the product of concentration of products divided by product of concentration of reactants, and whose coefficients that will be considered as power coefficients. Then for reactants also, whose coefficients will be considered as powers, right? Whose coefficients considered as powers, right? This is the law of chemical equilibrium. And similarly, instead of concentration, if we have to use partial pressure, so that is called Kp. Kp is equals to product of partial pressure of products divided by product of partial pressure of reactants, those coefficients which will be taken as their powers, then coefficients, right? So these are the Kc and Kp values, definitions from the law of chemical equilibrium. So we have to apply this for the chemical equilibrium reactions, right? So considering one equilibrium reaction, right? So for that we have to apply Kc and Kp, right? One example here, PCl5 is dissociates into PCl3 plus Cl2, and whose physical states also mentioned in the square bracket, right? So the physical states of all these will be gases only. Therefore we have to write the Kc value. Kc is the, how many products? Two products are there, the concentration of products, right? So that is PCl3 concentration, whose coefficient is 1, therefore 1. Then Cl2 concentration divided by PCl5 concentration, right? Similarly, the Kp value we have to express, all are gases only, that's why we have to utilize a partial pressure. The partial pressure of the gases products means P of PCl3 dot P of Cl2 by P of PCl5. This P means partial pressures, right? So whenever concentrations will be there and partial pressures will be there, the units of Kc and Kp, right? So the units of Kc and Kp can be written as Kc is equals to, concentration will be expressed in terms of moles per liter power its coefficients, that coefficients will be written as delta N, how many number of moles, right? So then Kp will be pressure, partial pressure will be atmosphere, and atmosphere power delta N. So what is meant by delta N is equals to number of moles of products, particularly gaseous, minus number of moles of reactants, right? Number of moles of reactants. These reactants also will be gases, right? So delta N will be number of moles of products and number of moles of reactants. number of moles of products minus number of moles of reactants, that will be substituted in moles per liter power delta n, we will get units of Kc, then atmosphere delta n will get units for Kp. Then we have to consider delta n for this example, right? So for PCl5, so the products will be, two products will be there, here the coefficient is 1, here is 1 and here is 1. So therefore delta n will be 2 minus 1, that is equals to 1 only, right? So therefore the units of Kc for this reaction, so that is moles per liter power 1, that becomes moles per liter. Then Kp units are atmosphere power 1, means atmosphere only. So these are the units we have to apply for this equilibrium reaction by considering Kc and Kp. And here we have to remember one term, that is for pure solids and liquids, right? So for solids and pure liquids, the concentration and as well as partial pressure is considered as unity. No need to consider those terms in the equilibrium constant. So therefore, so we have to apply for the various reactions involving in gaseous and liquids and solids. We are able to apply this equilibrium constant Kc and Kp, right? So now we will get the relation between this Kp and Kc. Right, so relation between Kc and Kp, most important, we are able to get the questions from this area, the relation between Kp and Kc, that we have to apply for the various reactions, right? So relation between Kc and Kp, right? So even directly we have to remember that relation, or else we have to prove that relation, right? So first we have to prove, and then later on we have to remember that relation between Kc and Kp, right? So now consider a reaction. The simple reaction, A is converted to, means A is equilibrium with B. A is equilibrium with B. How many moles of A is equilibrium with B? How many moles of B is formed, right? So AX is equilibrium with X moles of A is equilibrium with Y moles of B. X moles of A is equilibrium with Y moles of B. How many moles of A is involved means XA. How many moles of B is formed means Y moles of B. So again Y will be converted into A. B will be converted into A, that means reversible reaction, that is the equilibrium reaction. So for this we have to apply the equilibrium constant. So how will get equilibrium constant? That is expressed in terms of Kc. Equilibrium constant, so that is concentration of B power Y divided by concentration of A power X. So this is the equation number 1. So that is the Kc representation as we discussed that. So the concentration and whose coefficient will be taken as power, right? Here B concentration power Y, A concentration power X, right? That is equation number 1, that is the Kc. Similarly, we will get Kp value. Kp means partial pressures. Kp is equals to, we have to utilize partial pressure of B power Y by partial pressure of A power X. Partial pressure of A power X. So this is the equation number 2. But from ideal equation, PV is equals to nRT. So this is for n moles of gas. PV is equals to nRT for n moles of gas. So then P is equals to n by V RT. So this n by V will be, we know that active mass or else concentration. That active mass or concentration will be expressed with square bracket into RT. So therefore, whatever is the pressure we have to apply for the products and apply for the reactants. So therefore, this we have to written as the pressure of B is equals to concentration of B into RT. So then the partial pressure of A is equals to concentration of A into RT. So this is the equations we have to substitute in equation 2, right? Means equation 3 is substitute in equation 2. So we will get the relation between Kc and Kp, right? So even directly also we have to remember, but we have to know the concept how we are getting. Sometimes we will get confusion, either kp is equals to or kc is equals to. We have to overcome that confusion, means we go through the concept only. If you remember this concept, you not able to do the mistake during the examination, right? So pb value and pa value we have to substitute in equation 2, right? From equation 2, kp is equals to, right, pb means concentration of b into rt power y divided by concentration of a into rt power x, right? So therefore we are able to separate this concentration of b power y by concentration of a power x, concentration of a power x into rt power y by rt power x. So this is the value is kp is equals to b power y by a power x. B concentration power y by a concentration power x is equation 1, that is equals to what? Kc. Therefore from equation 1 we have to written as kp is equals to, this is the term that will be kc. Kc into rt power y, and this x will be come to the numerator, that becomes y minus x. So for this reaction we have to apply the delta n, means number of moles. So these are the gaseous molecules A and B. So therefore number of moles of products minus number of moles of reactants, that is y minus x, that becomes considered as delta Ng. Therefore delta n is equals to y minus x. Therefore kp is equals to kc into rt power delta n. This is the relation between kc and kp. Equilibrium constant in terms of pressures and equilibrium constant in terms of concentrations, how they are related with each other with respect to the gas constant, temperature and number of moles. This is the relation. Even we have to remember the relation is directly, that is kp is equals to kc into rt power delta n, where delta n is equals to product number of moles minus reactant number of moles. So based on this, with the help of this relation, right, so for many reactions the kc value will be more or kp value will be more, right? Either kc is more or kp is more, that is depending on the delta n value, right? So the relation, even in short form we have to written or remember, right? Short form means directly we remember the relation, that is kp is equals to kc into rt power delta n, right? kp is equals to kc into rt power delta n. So where delta n, some of the reactions which are containing delta Ng is 0. That means if delta Ng is 0, so when delta Ng is 0, right, delta Ng is 0, kp is equals to kc. We'll get both the rate constants, equilibrium constants will be equal. Kp is equals to kc, right? So if delta Ng is greater than 0, Ng also we have to write, or delta n. So because it will be applicable for the gases only, delta n is greater than 0 means delta n is equals to positive. At that time the kp is greater than kc, right? So then the third condition, if delta n is less than 0 or delta n is equals to negative. Less than 0 means negative values. At that time kp is less than of kc, right? So these are the three conditions where kp is equals to kc. So whether the reaction is consisting kp is equals to kc, that is depending on the reactants and number of reactants and products with the help of number of moles, that is a delta n, right? So when kp will be more means delta Ng value will be greater than. When kc is more means delta Ng value will be less than, right? So just we have to consider the examples. So then we have to apply all those conditions of this delta Ng and remaining things, right? We have to take one question, right? So what is the relationship between kp and kc? for the following reaction. What is the relationship between Kp and Kc for the following reaction? What was that reaction means? N2 is reacts with 3 moles of H2 is equilibrium with 2 moles of ammonia. This one is gas, hydrogen is gas, and nitrogen also gas. Right? So the options will be first one. So Kp is equals to Kc into RT power 2. Right. Second one, Kp is equals to Kc into RT power minus 2. Third one, Kp is equals to Kc into RT. Then fourth one, Kp is equals to Kc. Which one is correct? Right? So then we have to apply the conditions directly. We have to utilize that relationship between Kc and Kp. Just simply here we have to consider delta Ng or delta N. Delta Ng is equals to number of moles of products minus number of moles of reactant we have to consider. How many number of moles of products are there? That is 2. Minus how many number of moles of reactants are there? 3 and 1. Both are the gases, therefore we have to consider 1 plus 3. Therefore 2 minus 4, that becomes minus 2. Delta N is equals to minus 2. Therefore that we have to substitute in that equation. We will get the answer, that is Kp is equals to Kc into RT power minus 2. Right. Kp is equals to Kc into RT power minus 2. Right. Right. So next question. Which of the following is correct for which of the following is correct for which of the following is correct for the reaction H2 plus I2 is equilibrium with 2 moles of Hi. This is the gas and gas. Right. So the given options will be means, so what is the relation between Kp and Kc? So that is the which of the following is correct for this following reaction means the first one will be Kp is equals to Kc. Right. Second one will be Kp is equals to Kc into RT. Right. Kp is equals to Kc into RT. Then third one is Kp is equals to Kc into RT square. Right. So then the fourth one is Kp is equals to Kc into RT power minus 1. Right. So where also we have to get number of moles, delta Ng, change of number of moles during this reaction. So that is here the 2 moles will be there, here 1 and 1 stoichiometric coefficient. Therefore we have to consider delta Ng. Right. So therefore delta Ng is equals to N of products minus N of reactants. That is number of moles of products is 2 minus number of moles of reactants are 1 plus 1, that is 2 minus 2, that is 0. When delta Ng or delta N is 0, therefore the condition was Kp is equals to Kc is the correct. Right. So both equilibrium constant Kc and Kp are same. Right. So Kp and Kc are same. So this is the relation between the Kp and Kc that we have to apply for the various reactions. If delta Ng is less than 0, Kc will be more compared to Kp. If delta Ng is greater than 0, Kp will be more compared to Kc. Right. So then if delta Ng is equals to 0, both equilibrium constant Kp and Kc are equal. Right. So one previous question 2025 question will be there. So that is with respect to the graphical representation of equilibrium process. So for a one reaction, right? So even that is also we have discussed those concepts we have covered in the previous class, right? So the question will be, which of the following is correct representation? Which of the following is correct representation for given reaction? That is, N2 plus 3H2 is equilibrium with 2 moles of NH3. Right, all are gases. Right, which of the following graphical representation is correct for this following reaction? Right, so what are those graphical representations we have to see? Right, the first one will be time versus molar concentrations. Time versus molar concentrations, right? So here reactants are nitrogen and hydrogen, product will be ammonia, right? So here the hydrogen concentration will be decreases, right? Next, nitrogen concentration will be increases. Nitrogen concentration will be increases. So then ammonia concentration also increases. So this is the one representation, right? So then second one, molar concentration versus time. Time versus molar concentration. Time versus molar concentration. So where H2 will be decreases, concentration of H2 will be decreases, then concentration of N2 also decreases, then concentration of ammonia also decreases. So all the concentrations will be decreases. That is the second one. Then third one, the third representation of time versus molar concentration. Time versus molar concentration, right? So here hydrogen concentration will be decreases, then nitrogen concentration will be decreases, then ammonia concentration will be increases, right? So then the fourth option will be the representation of time versus molar concentrations of those reactants and products, right? So here N2 will be decreases, hydrogen will be increases, and nitrogen ammonia also increases, right? So this type of plots are given in the options, right? So just see here what are the reactants. So the chemical equilibrium means with respect to the concentrations means the concentration of reactants is decreases and the concentration of products is increases, right? At the condition where the concentration of products is equal to the concentration of reactant, that is the condition is known as equilibrium condition. Here we are getting the equilibrium between nitrogen, hydrogen and ammonia, right? So hydrogen and nitrogen gases will be decreases, right? Reactant concentration is decreases, at the same time product concentration is increases, right? See here, hydrogen decreases, nitrogen increases, therefore this is wrong way, right? Hydrogen, nitrogens are decreases, at the same time ammonia also decreases with respect to time, means that is the wrong, because ammonia is the product concentration will be increases, right? So here hydrogen is decreases, nitrogen decreases, then ammonia will be increases, right? So therefore these concentrations of H2 and N2 is equals to ammonia concentration. At that particular condition we are able to get the equilibrium between the nitrogen, hydrogen and ammonia gases. Therefore this is correct. Why this will be wrong means nitrogen will be decreases, hydrogen will be increases, right? So even we will get 2025 June, right? 2025, so January question, right? So this is in IIT mains 2025 question, the graphical representation for equilibrium reaction. And also somehow questions we covered that, so that is relation between Kc and Kp, right? The relation between Kc and Kp. So two reactions. So this is the one reaction. H2 plus I2 gives rise to 2Hi, and one more will be PCl5 is equilibrium with PCl3 and PCl2 and Cl2. PCl3 and Cl2, right? So one more example we have to consider, one more question. So that will be indicates the relation between equilibrium constants, right? So that is, next question will be, what is Kp by Kc? What is Kp by Kc value for the following reaction, right? So that is sulfur dioxide plus oxygen is equilibrium with sulfur trioxide. 2 moles of this and 2 moles of this, right? 2 moles of this, 2 moles of SO2 plus 2 moles of sulfur trioxide, 1 mole of oxygen. All are gases, right? All are gases, right? So then the options will be right. Kp by Kc is equals to RT. Kp by Kc is equals to 1 by RT. So Kp by Kc is equals to root RT. So 1 by root RT, right? So these are the 4 options are given, right? So the relation between Kc and Kp we have to calculate, then the ratio of Kp by Kc will do. So whatever is the value is equals to which of the following options correctly, right? So just that will verify, right? So here we have to calculate delta N, that is the number of moles products minus number of moles of reactants. Here number of moles of products will be 2. So here the reactants will be 1 plus 2. So therefore 2 minus 1 plus 2, that is equals to 2 minus 3, that is equals to minus 1. Delta N value is minus 1. Therefore the relation between Kp and Kc, Kp is equals to Kc into RT power delta N. So therefore Kc into RT power delta N means minus 1, right? Delta N means minus 1, which is Kp is equals to Kc. But our question was the ratio of Kp by Kc. Therefore Kp by Kc is equals to RT power minus 1. Therefore we can written as 1 by RT. Therefore the ratio of Kp by Kc is equals to 1 by RT. So this is the one, right? So like that any equation will be there, equilibrium, right? So we have to get the relation between Kc and Kp. So with the help of relation, this Kp is equals to Kc into RT power delta N. The ratio of Kp by Kc or the ratio of Kc by Kp, right? Or else delta Ng relation, or Kp is greater than or Kc is greater than, right? So then what about Kp and Kc relationship? So that we have to apply for the various equilibrium reactions, right? So this is the representation of equilibrium and the how to write the equilibrium constant in terms of concentrations and in terms of pressures, that we have discussed already based on the law of chemical equilibrium and law of mass action, right? So two laws are there, law of mass action and law of chemical equilibrium. With respect to that we are able to write the equilibrium constant, right? Why we are going to get the equilibrium concept means what it will explains, what are the characteristics of the equilibrium constants, right? So that equilibrium has the characteristics. What are those characteristics of equilibrium? Let us discuss, right? So these are the previous year's questions covered, right? Right. So then we have to discuss the characteristics. Characteristics of equilibrium, right? So the first one will be dynamic in nature. Dynamic in nature. What is meant by dynamic in nature? Means equilibrium is dynamic in nature. So what we have to say, dynamic in nature, right? So that is the rate of forward reaction is equals to rate of backward reaction. Rate of forward reaction is equals to rate of backward reaction. This is happened at equilibrium. At equilibrium, the rate of forward reaction is equals to rate of backward reaction. Therefore, such equilibrium is dynamic in nature. That is the first characteristics, right? Next, the equilibrium does not affect by pressure, concentration, intensity of color, right? Intensity of color, density, and so on, etc. Right? So equilibrium does not affected by these properties like pressure, concentration, intensity of color, density, and so on. But whenever the temperature will be vary, right? So that equilibrium depends on temperature. Right? So the relation between the equilibrium constant and temperature, that can be explained with the help of Van 't Hoff's equation. So that can be given by logarithmic of equilibrium constant K2 by equilibrium constant K1. Log K2 by K1 is equals to 2.303, right? So 2.303 delta H by R of 1 by T1 minus 1 by T2. So this is the Van 't Hoff equation, right? So how the equilibrium constant is relation with temperature, right? If it is exothermic process or endothermic process, so how the equilibrium constants will be carried out, right? So means in synthesis of ammonia, right, some amount of heat will be liberated, so that is exothermic process, right? In some other cases, endothermic process, we have to provide that heat, then only the reaction was carried out, that is the endothermic process. Whether exothermic process or endothermic process, how the equilibrium constant will be varying, how the equilibrium constant is varying with respect to temperature, that we have to explain with the help of Van 't Hoff equation, right? And also which will be expressed, right, the extent of the reaction and the direction of the reaction, even that concepts also we have to explain with the help of characteristics of equilibrium constants, right? One will be dynamic in nature, and the rate of forward reaction is equals to rate of backward reaction. These are not affected properties, and equilibrium is affected by the temperature. That relation between the temperature and equilibrium constant will be explained with the help of Van 't Hoff equation, right? If both the temperatures are same, therefore equilibrium constants are also equal, right? Equilibrium constants are also equal. If it is a exothermic process, it is a endothermic process. So as endothermic process will be there, the temperature is increases, right? So if these temperatures will be constant, means the same temperature, right? So one second, right? If the temperatures will be, temperature T1 is equals to T2, if temperatures will be same, right? So therefore log of K2 by K1 is equals to 0. So therefore this is log K2 minus log K1 is equals to 0. Log K2 is equals to log K1. Therefore those equilibrium constants K2 is equals to K1. Equilibrium constant K2 is equals to K1, right? So when temperatures are same, if temperature difference will be there, right? So if you consider T1 is greater than, right, if T2 is greater than T1, right? So what about the temperature difference? We will get T2 minus T1 is equals to positive. This is the higher one, this is the lower one. T2 minus T1 is positive, so that positive means endothermic process. For endothermic process, as temperature is increases, the equilibrium constant also increases, right? So then the third condition, if temperature T2 is less than of T1, T2 minus T1 is equals to negative. So this negative means this is the exothermic process. So for exothermic process, as temperature is increases, equilibrium constant is decreases. That's why if both the temperatures are same, so at the time equilibrium constants are same, right? If one temperature will be high, temperature will be low, means T2 is greater than T1, so that is gives endothermic reaction. For endothermic reaction, as we can increase the temperature, equilibrium constant also increases. If it is exothermic process, the equilibrium constant, temperature is increases, equilibrium constant is decreases. So that's why there is a temperature effect on equilibrium constant that can be explained with the help of Wandt-Half equation. So that equilibrium constant will be explained with the help of Wandt-Half equation, right? So these are the characteristic properties. In addition to these characteristic properties, so some other good applications will be there. So whether that equilibrium will be in reverse manner, right? So for example, in direction one reaction is carried out, so that reaction is present in equilibrium. If that reverse reaction we need to consider, so what is the equilibrium constant value will be vary, right? So there are various number of applications will be there, so somehow we have to discuss. So based on that applications, numerical problems also we have to cover, right? Okay, then so the next application will be if A is equilibrium with B. A is equilibrium with B. At that time the equilibrium constant is K1. At the time the equilibrium constant is K1, right? So how will write this K1? That is the concentration of B by concentration of A in terms of concentrations. If we have to pressure PB by PA, right? So if the reverse reaction is carried out, that means B is equilibrium with A. So what is the equilibrium constant? This K2 will be, how will express it in terms of K1 means A concentration divided by B concentration we will get, therefore so we have to get that is the 1 by K1, right? So means whenever the reaction becomes reverse, right? So the equilibrium reaction becomes reverse. A is equilibrium with B. For that equilibrium constant is K1. But now we have to consider the reaction is reverse reaction, that is B to A. So that is 1 by K1 will give the equilibrium constant of this particular reaction. That is the one application, right? Next, if A is equilibrium with B, at the time whose equilibrium constant is K1. Whose equilibrium constant is what? K1. So therefore this K1 how will write? Concentration of B by concentration of A. If this concentration, number of moles of reactants A and B will be double, that means 2A is equilibrium with 2B, right? Number of moles will be increasing, so this coefficient will be came as powers, right? So therefore this will be K2 will be, we have to written as K1 power 2. So now coefficients 2 will be there, therefore K2 will be equals to K1 square. Or else if half that reactant, right, so that is 1 by 2 of A is equilibrium with 1 by 2 of B. If we consider this reaction, if consider that is K3 is equals to what? K1 power 1 by 2, right? Or else we have to take square root of K1. So these are the simple applications, right? If we need to reverse, so that is by doing 1 by only. So for this reaction only, right, A is gives rise to B, what is that? K1 will be there. Now I need to consider for 2B is equilibrium with 2A. Right, A to B is K1, therefore B to A means 1 by K1. So 1 by K1 we have to do, and also number of moles also varying. So therefore in this case what we are getting means that is 1 by K1 square. So because 2 will be there, right? So for M moles we have to consider, right? So that becomes MA is equilibrium with MB. So therefore, so that K equilibrium constant of Kx, some x terminology we have to utilize. So that is K1 power M, right? So that is, so same so this we have to consider the reference one. MA is equals to MB means same will be there. A to B is there. A to B. If it is reverse, 1 by we are getting. Therefore, Kx is equals to K1 power M. This may be 2 moles or 3 moles or 4 moles or many number of moles. Whether the reaction is reverse reaction or reaction is same continuous reaction with various number of moles changing, right? So then it will be continuous reaction, simultaneous reactions. A is gives rise to B, B is gives rise to C, C is gives rise to D. Then how will get A to D equilibrium constant? So like that, huge number of applications of equilibrium constant are there in equilibrium reactions, right? So even somehow equilibrium reaction characteristics will be there in addition to this. So in the next class we are able to discuss the remaining applications of characteristics of this, and based on this we are able to solve the numerical problems, PYQs problems in next class. Until then, take care.